Hello everybody, my name is Antti Hyvärinen and I'm going to talk about how we used Lookahead in partitioning SMT instances. This is a joint work with Matteo Marescotti and Natasha Sharigina. Now the scope of this work is in parallel SMT solving, so this is something that in my opinion is becoming increasingly relevant as a result of this widely available parallel executing environments. I'm mainly talking about Amazon EC2 here. For instance, in 2021 SMT competition, we had the first time the possibility to run SMT solvers that competed in a truly parallel setting. We had two tracks, the parallel track with 64 virtual CPUs and then a cloud track with 1600 virtual CPUs. Each solver had all these CPUs available for solving a single instance, and then we repeated this for a couple of instances. Now in this competition, we had the parallel implementations of some of the best solvers around. We had CVC5, OpenSMT, which is our solver, PAR4, which is a portfolio solver, STP, which is more like a SAT solver, and Vampire, which is a theorem prover. Now often, even though not always, the parallel solvers perform better than the best sequential solvers, which is quite a good result already. If we want to have a look at the results, I've got this in this URL. I'm collecting some experiments, and give me feedback if you want to. But in this particular talk, I'm going to try to address the question on how to best achieve scalability, which with this increasing availability of the computing resources is becoming really relevant. So for me, this question of parallelizing SMT solvers goes back to roughly to this question whether to do portfolio or divide and conquer. So in algorithm portfolio, the idea is to run a set of solvers in parallel on the same instance. And then you terminate once one solver determines the satisfiability. You can share information between the different solvers, of course, in addition to that. Whereas in divide and conquer, you partition the search space of an instance to mutually disjoint parts. So this is already something more complicated that is happening. Then the approach terminates when one solver has shown satisfiability or all partitions have been shown not to contain solution. So there's even more complicated termination condition for the divide and conquer. And on top of that, you can also, of course, share the information, but then you have to make sure that the information that you share is actually valid in the target partition. So yet another complication for sharing information compared to algorithm portfolios. So to be more practical, I here have a picture where I'm comparing. These are results from this year's SMT competition, and I'm comparing OpenSMT with partitioning against sequential OpenSMT. So I just picked OpenSMT because it's our solver. I know how it works. So looking at these results, you can say that divide and conquer is way better than the sequential version. So we get, if we sum up all the runtimes for each solver, we get a speed up of roughly threefold. But not only solve we solve the instances faster, but we actually solve more of them as well. So we, on the set of instances that in this case consisted of 32 instances, we can solve 6 more instances with a partitioning. And the crosses are satisfiable instances and boxes are unsatisfiable instances throughout the presentation. Okay. Now, if we compare the result with this partitioning result with a portfolio, the similar implementation of OpenSMT with portfolio, we can see that the results are a little more nuanced than that. So I claim here that there is no clear winner between the divide and conquer and portfolio. Now, you could say that portfolio is faster, and it clearly is in most instances, but at the same time, divide and conquer manages to solve one more instance and then the portfolio could not solve. So in this presentation, I would try to study this question of how the divide and conquer works in SMT. So I already mentioned that divide and conquer is complicated to implement, and there's many potential reasons how to explain this kind of a relative slowdown in SMT. We'll see later on that it's not just a relative, but an absolute slowdown as well. But so first things that come to my mind could be communication delays, construction of partitions takes time, maybe suboptimal partitions. Let's say you construct a lot of easy partitions and then combine with the communication delays, you get like a slowdown just because you end up using so much time communicating. Or you could have, let's say you're working on a shared memory system and you have just the memory access becomes a bottleneck. You have too many threads running at the same time, so that gives you a slowdown. But it could also be something a little more complicated. So, for instance, it could be statistics-based slowdown in unsatisfiable instances in particular, where you have to wait for the longest running instance, and the instance runtimes are kind of stochastic anyway. So that tends to push the runtimes towards the more difficult instances. Or it could be proof theoretical reasons. For SAT, we have a result that if you fix the branching heuristic branching order of literals, you can get a super polynomial slowdown of separation between two proof systems. And we're kind of doing a similar thing here with the partitioning when we fix literals. Or it could be incomplete understanding of the real search space in SMT, which is also hard to define, even harder to define than in SAT, where it also is very hard to define. And so in this talk, we attempt to exclude some of these simpler reasons and still show a slowdown, indicating that there's something quite interesting happening in practice in these instances and these searches. So the presentation rough outline is in here. We first have a look at DPLL, the classical SAT solving algorithm from 60s. How you can do Lookahead on that one, done in the 80s. And then we jump to a much more recent result, how to do CDCLT, which is the conflict-driven clause learning SAT solving algorithm combined with SMT solvers. How to use Lookahead on that algorithm. And then to the actual contributions of this paper, so how to do partitioning with the CDCLT Lookahead, and then the experimental results. I use quite a lot of time on the first part to try to convince ourselves that the Lookahead CDCLT combination is actually a good way to do partitions, so we don't have these suboptimal partitions. And finally, with the experimental results, I can rule out the memory congestions and construction of partition is costly and communication delays, these kind of more trivial reasons, just by designing the experiments correctly. So let's first have a look at the DPLL algorithm. As input, the algorithm takes a SAT instance in conjunctive normal form. I've written here an example of that. That's 5 clauses and a couple of variables. And it constructs this DPLL search tree, where we have 2 types of literals and branches. So we have decision literals that I indicate in red, and the gray ones are the propagated literals. So these decisions are heuristically chosen among unassigned literals, and the propagations occur when all but one literal in a clause is assigned to false. You can see here, for instance, looking at the first 2 clauses, we have not x or y and not x or z. And if we branch on x to satisfy y and z, we have to set them true. The first 2 clauses, we had to set y and z to true, and this gives this is called a propagation. Okay. Finally, we have conflicts that occur when propagation forces a literal to be both true and false. So in this case, we after choosing x and not v, we can propagate among others w and not w, which is a conflict. And conflicts are useful because they prune out unsatisfiable search spaces, and in the end, that is what we want to do. We want to prune all the branches of the DPLL search tree to show an instance unsatisfiable. So to do Lookahead in DPLL, the idea is to, before committing to a decision, so before choosing what kind of a tree we're going to build, we see how many literals would propagate as a result, and then we commit to the result that is the decision variable that or literal that results in most propagations. So looking at this example in here, if we branch on x, we get x, z, and y. So and if we branch on not x, we may look first at x, for instance, in both polarities. Not x gives no propagation. So we can compute the kind of a Lookahead score. For x we get 2, and not x we get 0. And then maybe we commit to x because that seems to be reducing the search space more. And then we can do the same thing, for instance, for variable v. We check v and not v, And now something quite interesting happens. So for V we get no propagation, so the score is 0. For not V we instead get a conflict, the same conflict that we got before. And then we have to decide what to do with that. So the DPLL algorithm changes a little bit because of the early conflict detection that we have in it. Then looking at how to do this Lookahead in CDCLT, things get even more interesting. So most SMT solvers are driven by this conflict-driven clause learning SAT solver. And this CDCL algorithm differs significantly from a DPLL-style search. First of all, the algorithm learns clauses using resolution. And then when you put it to an SMT solver, the SMT solver in addition learns theory lemmas. So the search space is changing. We have new clauses coming in. There also is no search tree in the sense of a DPLL search. So to be more concrete about it, let's have a look at how the CDCL algorithm works. So there's a search phase. We organize the search as a stack of decisions and propagated variables again. So I've got here on the left I have the CDCL stack. On the right I have the DPLL tree just for comparison, and then in the middle the instance. So if we choose to branch on X, we propagate, we put these propagations on the stack, and then we can continue choosing, let's say, the not V, and we propagate again the U, W, and not W, and we have the conflict. And then we need to do, again, something for the conflict. So in CDCL, what happens after a conflict is that the algorithm learns a clause. And how this happens is by constructing a conflict graph. So a conflict graph is a graph where the nodes are literals, and of course there's two types of literals. And a propagated literal has incoming edges from the propagating clause. So we know that each propagated literal gets propagated by a clause, and we have an edge from each literal in the clause to that propagated literal. In addition, each of these literals is labeled with a decision level, which is based on the number of decision literals in the stack below this particular literal. So if you follow what I just said, you could build this kind of a conflict graph from the example, the stack and the instance that I have. So this graph is then partitioned into two parts: the conflict side and the reason side. And these two parts are separated by a cut. So the conflict graph will be used to guide resolution that derives the learned clause. And the learned clause needs to have a single literal at the highest decision level. So if I draw here a cut, this cut, I claim that it defines a clause for us. And how does it define the clause? Is that you take each of the edge that cross from the reason side to the conflict side. And the sources of these edges will be literals in the clause. We do operations on this clause, on this cut, because we need the learned clause to have a single literal at the highest decision level. And the operations that we do to achieve a clause like that are to move literals from the reason side to the conflict side. So what we can do in here, so first of all, this cut does not satisfy the condition because there are two literals at the top decision level, U and not V, on the reason side. And we can move U to the other side of the cut, resulting in this. And now this cut corresponds to a correct learned clause because the highest decision level on the reason side is 2. What happens next is that we take the literals on the reason side and we negate them, and that gives us the clause. So in this case it will be not Z or not Y or not or V. This clause will then be used in the next phase, which is backtracking. So we look at the clause that we just learned and the decision levels in it, and we clear the track to the highest decision level that appears in the conflict. So in this case, the second highest decision level that appears in the learn clause, I mean to say. And in this case, it is 1. So we clear the track. By removing everything starting from not v, which is the decision level 1 and 2. And now, because the conflict clause contains a single literal at the highest decision level, it is guaranteed to propagate a literal. So in this case, it'll propagate as v. And this way we have made advance in the search, similarly like we did in the DPLL tree, but in this case in a more abstract way by adding new clauses to a decision level, new literals in the decision level. So how can we use this algorithm that I just described together with a DPL with a Lookahead? Now, my idea here is that we still keep on doing the DPLL search tree, and we do a DPLL search tree style object, but we use the CDCLT to compute the Lookahead values in this when we expanding the tree. And we let the CDCLT state of the solver evolve, so that when we learn clauses, the theory and theory lemmas, they affect the Lookahead scores. And then we use the evolving state to prune partitions that are newly discovered unsatisfiable. So let's have a look at the CDCLT Lookahead algorithm now, I mean more concretely. So we build the DPLL tree depth first. And the idea is that we expand the tree in some node. So we place the CDCLT solver to a given node by doing the assumptions that are implied by the path to the node. And then on that point we compute the Lookahead score. It might mean that we backtrack. We might learn clauses in the case of conflicts. If we don't do that and we manage to do a full Lookahead, we can choose the best literal according to the Lookahead. However, if we can't do that, then that means the CDCLT solver may have encountered or will have encountered a conflict and needs to backtrack to resolve them. And the CDCLT algorithm may have to backtrack several levels on the DPLL tree that it's building. And that means that it's forced to rebuild these parts of the tree. And every time we do the Lookahead phase, it means that the solver state might change actually significantly, because we do a lot of choices and potentially a lot of learning as well. So how do we do then this? How do you apply this idea for splitting? The idea here is fairly straightforward. We just construct the DPLL search tree depth first, just like in the original algorithm, the Lookahead based CDCL. But we limit the depth of the tree to n, where 2 to n is the desired number of partitions. And we use the CDCLT solver to guide the construction of the DPLL tree, just like in the CDCLT Lookahead algorithm, okay? And what is nice about this design is that it naturally gives a splitting algorithm that is guaranteed to either produce exactly the 2 to n splits that we asked for, or then to solve the instance by showing it unsatisfiable or satisfiable. So that's the algorithm that we're going to use for splitting. Now I go to the experiments. The instances we're taking from SMT logics, QF-LRA and QF-UF. And we chose these two logics because they are quite fundamental in the SMT solving. So they exercise the three algorithms that are widely used in practical SMT solving as well. So the CDCL algorithm that is used in both QF-LRA and QF-UF. And then the simplex algorithm that is used in linear real arithmetics, obviously, and the congruence closure algorithm that comes from unintuitive functions. And we try to select instances that are hard. So it means that these instances are, with OpenSMT, we need at least 100 seconds to solve them. Now there's a bit of a catch in here because OpenSMT is quickly getting a better and better solver. So recent improvements result in some of these instances not being so hard for OpenSMT anymore. But still they take more than 10 seconds to solve, at least. Okay, so the experimental setup here is as simple as possible. Intentionally, we take an SMT instance and this Lookahead partitioner, that is a little bit complicated object as such, and let it do as this partitions P1 to Pn, where n is a power of 2, and then we just distribute the instances to each to one solver. So then we define the runtime of this procedure part n as if the instance is satisfiable, then it is the shortest runtime of any of the solvers that find this solution or a solution. And if the instance is unsatisfiable, it'll be the longest runtime of any of these solvers. So in particular, the runtime of part n does not include the communication delays or the time to partition. And then the partitions are inserted as is to the SMT solver. So that means that we don't use incrementality to insert them, and therefore we don't introduce any overhead related to the incrementality either. So I have here a practical example. These are the instances in our experimental set from quantifier-free uninterpreted functions. It's a scatter plot comparing part 2, so partitioning into 2 parts, and the sequential algorithm. And just to give some context, I put the twofold slowdown there. We can see that the results are actually pretty good. No surprises in here. We got 3 instances here that get slightly more difficult to solve with the partitioning once we partition in 2, so that's kind of weird. But then again, it looks like these are just random noise, because if I partition them to 64 parts, then all of a sudden it actually works pretty well. The situation comes quite a lot different if we look at the quantifier-free linear real arithmetic instances. So we can still say that in general the approach works quite well. But then there are these non-trivial slowdowns. So I'm of course talking about these instances here. We have both unsatisfiable and satisfiable instances that actually get more than 2 times slower to solve. So let's have a closer look at 2 of these instances actually. So I first take the satisfiable instance here and plot the median solving time as a function of number of partitions that I create. So we can see here that, as it was in the previous picture, that when you partitioned it into 2, the instance actually got a little bit more difficult. So you can see here the increase before the speed up, let's say. The speed up happens at 4 partitions, and then the situation kind of slowly goes down, but it's kind of stable after that. So to understand a little more about this, I can plot the individual runtimes of the partitions. So the green crosses are the runtimes for each partitions, and they are now grouped around the number of partitions that I create, and then they are sorted from easy to hard, so that they are a little easier to see. And what we could see in here is that when more partitions are created, the partitions kind of split into 2 groups. So there are the unsatisfiable instances that are the easy ones, and satisfiable instances that are harder. And as we keep on producing more partitions, the unsatisfiable instances, some of them keep on getting harder and harder. This is maybe not so surprising, because the unsatisfiable instances, so when an instance is satisfiable, it's usually easier to find the satisfiable assignment than to prove it unsatisfiable. So if we rule out the satisfiable solutions altogether, then it probably means that the unsatisfiable ones are going to be quite hard. And but interestingly, the more and more we put constraints into these unsatisfiable instances, the harder they seem to be getting to solve. So we're already seeing in this satisfiable instance quite some interesting behavior, up to 2048 partitions, which is already quite a high number. I can add a little more information here by showing, because I ran each of these instances, each of these partitions, a couple of repetitions on them with a randomized solver. And this way I can get a distribution, which is marked by these blue lines in here. So we can see here that when we have an overlap with the partitions, that suggests that we've kind of managed to do a good partitioning. And usually that results in a speed up as well. We can see quite clearly the increase in difficulty for partition 2 also in this for part 2, also in these distributions. Finally, I can visualize this situation a little more with by simply repeating the solving of a run of this part in approach. And here each of the boxes is a single run, And then I can compute the minimum, medium that I already reported, and maximum of the runtimes. So we can see here quite clearly the part 2 is harder than the original instance. Another interesting thing in here is that when we increase the number of partitions, it kind of looks like the instance is indeed getting easier. But on top of that, it is also the spread of the instance is getting smaller and smaller. So we have this stabilizing effect also in partitioning happening in here. So that was a satisfiable instance. Now let's have a look at unsatisfiable instance. So I plotted here similarly the median as a function of the n in part n. Okay, and we can see now a runtime increasing up to 512 partitions. The instance seems to be getting harder and harder than the original one, and then all of a sudden we have this collapse when we double the number of partitions. Again, plotting the runtimes of individual partitions, we can see that often there's a handful of hard partitions and the rest are relatively easy. But it's still there. The hard ones are, and there's quite a few of the hard ones as well. Again, I can plot the difficulty, and here we see something quite interesting in my opinion, that the instances, maybe the hard ones even, kind of seem to be having this wide range in which they are solved. We still see this maybe an effect of them getting harder and harder while we split, but what we definitely see is this drop in the difficulty. So that seems to be existing there, that if you have high enough number of partitions, then the difficulty will collapse. And we can see somewhat similar effect in here when we plot the runtime of the part n, the minimum, maximum, and median runtimes, and the plots related samples. So they are more biased on the low ones. So they're usually faster, these runtimes, but still they are the high outliers as well. But we definitely can see the instance becoming easier after the 1024 partitions. So one thing that you might be interested in as well is how hard it is to actually compute these partitions. And I show here the results for both uninterpreted functions and linear real arithmetics. And the good news is that for uninterpreted functions it is quite efficient. So in the vast majority of the cases we have the partitioning done in 16 partitions in this case under 1 second. But there are some outliers. And the not so good news is that for linear real arithmetics it seems to be quite expensive. So half of the time we can do it in less than 10 seconds, but then there are some outliers that take a lot of time. Now I have to say that the implementation is not particularly optimized. And you might be interested in also seeing where were the anomalous instances that I showed a little while ago. So they tend to be on the harder side of the partitioning algorithm as well. So this concludes the presentation. I think I could show you that using divide and conquer algorithms in parallel SMT solving is in general a good technique to obtain speed up. But even when we use a good lookahead heuristic, I'm claiming that the lookahead heuristic here is quite good for this purpose, there may be these surprising slowdowns, especially with the simplex-based QFL array algorithms. Partitioning to many parts seems to not only make solving often the faster, but even when it doesn't make it faster, it decreases the randomness in the runtime, which is kind of a positive thing as well. And finally, the lookahead-based partitioning in CDCLT is relatively expensive, but I'm still kind of optimistic that approximative algorithms and a bit of optimization can make this approach also practical. So that's my presentation. I hope this kind of raised your interest in the topic, and I hope you enjoyed it. Thank you.